There's a moment happening right now in our solar system that won't repeat for another generation, and it's already making waves in ways that blur the line between confirmed science and controversial theory. January 9th, 2026. 3 celestial bodies, the Sun, Venus, and Mars, are aligning with such precision that they fit within a single degree of sky. Stefan Burns claims this geometric trigger is unleashing solar fury toward Earth, coronal mass ejections, and plasma filaments racing across 93 million miles of void. Others say it's coincidence, that planets can't influence stars, but instruments are detecting elevated activity, seismic patterns are shifting, and a full halo signature has appeared. Stay until the end, because the question we're really asking isn't just what's happening. It's whether we've been missing something fundamental all along. You'll want to subscribe and follow along as new data continues to stream in, because what's unfolding in the space above us carries implications that official channels aren't quite ready to discuss openly. Something is stirring in the void between Earth and the Sun, and right now, as you're hearing these words, a sequence of events is unfolding that hasn't occurred with this exact precision in over 40 years. The date is January 9th, 2026, and 3 celestial bodies are converging into a configuration so tight, so geometrically perfect, that astronomers are calling it a once-in-a-generation triple conjunction. The Sun, Venus, and Mars are aligning within a single degree of apparent separation, creating what appears to be a cosmic bullseye in our sky. If you could somehow shield your eyes from the sun's overwhelming glare and peer directly at this alignment, you would see 3 worlds stacked almost on top of each other, a planetary sandwich of fire and rock compressed into a sliver of space no wider than your pinky finger, held at arm's length. Geophysicist Stefan Burns has been tracking this alignment for months, and what he's observing has sent ripples through both mainstream and alternative science communities. Burns claims that this geometric convergence is not merely a visual curiosity, not just a cosmic coincidence we can admire and forget. According to his analysis, this triple conjunction is acting as a trigger mechanism, somehow unlocking a torrent of solar fury directed squarely at our planet. Multiple coronal mass ejections, those billion-ton clouds of magnetized plasma that the sun occasionally hurls into space, are allegedly racing toward Earth right now. Plasma filaments, those towering arcs of superheated gas that loop above the solar surface like bridges made of fire, are reportedly erupting and launching their contents into the solar wind stream that flows past our world every second of every day. The imagery coming from solar observatories paints an unsettling picture. Current telescope feeds show the solar disk peppered with active regions, those darker patches where magnetic fields twist and tangle like knotted rope about to snap. Filaments hover above these regions, suspended by invisible magnetic architecture, looking for all the world like dark scars cutting across the sun's face. These structures are always present during active phases of the solar cycle, but what has observers on edge is the timing and the intensity. Space weather forecasters are reporting elevated solar wind speeds, higher than the baseline we've seen for weeks. Plasma streams are accelerating, pushing outward from the sun in waves that will arrive at Earth's doorstep in anywhere from 1 to 3 days, depending on how fast they're moving. NASA's official bulletins, released as recently as January 4th, describe the current solar activity as C-class flares, which sit near the middle of the flare intensity scale. These are not the monster X-class events that can knock out satellites and scramble communication systems, but they're significant enough to warrant attention. The Space Weather Prediction Center notes that elevated solar wind conditions are already buffeting Earth's magnetosphere, that invisible magnetic shield that protects us from the worst of the sun's particle radiation. Filaments are indeed present and active, but here's where the narrative splits into 2 paths. Official sources have not yet confirmed any major Earth-directed coronal mass ejections. The coronagraph instruments that watch for these eruptions show activity, yes, but nothing that screams imminent danger on a civilization-threatening scale. Yet there's a claim circulating that demands our attention, one that exists in that uncomfortable space between verified observation and speculative interpretation. Burns and others point to what they call a full halo shockwave, a specific signature in coronagraph imagery that suggests a CME erupted from the far side of the sun and produced a halo effect encircling the entire solar disk. When you see a halo CME, it can mean one of two things. Either the eruption is heading directly toward Earth, expanding outward like a cosmic shotgun blast aimed at your face, or it's heading directly away from Earth, receding into deep space where it poses no threat to anyone. The geometry of observation creates this ambiguity, this maddening uncertainty where you see the effect but cannot immediately determine the direction. As of this moment, verification is pending. The scientists who monitor these events 24 hours a day are analyzing data streams, comparing observations from multiple spacecraft positioned at different angles around the sun, trying to triangulate the true trajectory of any plasma clouds that might be heading our way. What we can say with confidence is that geomagnetic storm conditions are forecast for the coming days, likely reaching G1 or G2 levels on the 5-point scale that measures how much the sun's tantrums shake Earth's magnetic field. At G1, you might see auroras at higher latitudes than usual, those shimmering curtains of green and red light that paint the night sky when charged particles collide with atmospheric gases. Radio operators might notice interference on high-frequency bands. At G2, those auroras push further toward the equator. Power grids in higher latitudes might experience minor fluctuations, and spacecraft operators start paying closer attention to their systems. These storm levels are plausible based purely on the elevated solar wind conditions already confirmed by instruments in space. You don't necessarily need a massive CME to create G1 or G2 storms. A fast stream from a coronal hole, those regions where the sun's magnetic field opens up like a tear in fabric, can deliver enough of a punch to light up the auroras and rattle our communications. The question hanging in the air, the one that makes this situation more than just another routine space weather event, is whether something bigger is coming, whether the conjunction timing is pure coincidence, or whether we're witnessing a phenomenon that standard solar physics hasn't fully explained. Burns goes further, connecting this solar activity to another phenomenon that mainstream science treats with extreme skepticism. He notes that seismic activity around the globe has ticked upward in recent weeks, suggesting that the influx of energy from enhanced solar wind might somehow be triggering or amplifying earthquake activity. The official scientific consensus on this idea is clear and unambiguous. Earthquakes are driven by tectonic processes, by the grinding collision and separation of continental plates, by the release of accumulated strain in Earth's crust. Space weather, according to every major geophysical institution, does not cause earthquakes. The energy scales don't match, the mechanisms don't connect, and decades of data show no reliable correlation between solar storms and seismic events. And yet the idea persists, fueled partly by anecdotal observations and partly by the human tendency to find patterns even where none exist. When something dramatic happens in the sky, at the same time something dramatic happens on the ground, our brains want to link them, to construct a narrative where cause flows smoothly to effect. It's a very human impulse, one that has driven both great discoveries and great misconceptions throughout history. So here we stand, watching these three worlds align in the sky, watching the sun spit fire and magnetism into the void between us, waiting to see whether this confluence of geometry and energy is simply a mild cosmic coincidence, or whether it represents something stranger, something that hints at connections we haven't yet mapped in our models of how the solar system operates. Could there be hidden triggers, subtle electromagnetic couplings that only manifest under specific geometric conditions? Could the conventional picture of an inert solar system, where planets orbit silently without influencing their parent star, be missing something fundamental about how energy and information flow through the electromagnetic environment of space? These questions hover over the data, like the plasma filaments hover over the sun's surface, charged with possibility, waiting for the next observation to either confirm them or sweep them away. The coming days will tell us more as instruments track the speed and density of the solar wind streams now racing across the 93 million miles that separate the sun from Earth, as magnetometers on the ground measure how much our planet's magnetic field compresses and flexes under the bombardment, as auroras either flare into brilliant displays or fade into disappointment. But the story doesn't end with what hits us or doesn't hit us in the next 72 hours. The story expands outward from this moment, pulling us into deeper questions about how the sun works, about what planetary alignments might or might not do, and about whether the universe operates on principles slightly stranger than the ones printed in textbooks. The geometry of this alignment deserves closer examination, because precision matters when you're trying to determine whether three moving targets in the solar system can somehow influence the star they orbit. Venus reaches superior conjunction on January 6th, 2026, meaning it passes behind the sun from Earth's perspective, disappearing into the solar glare as it moves along its orbital path on the far side of our star. Mars follows close behind in this cosmic parade, coming into its own conjunction just days later. The result is a configuration where both planets and the sun occupy nearly the same line of sight from Earth, compressed into that single degree of apparent separation. It looks intimate, almost claustrophobic, as if these worlds are crowding together for a family portrait in front of the sun's blazing backdrop. But here's where we need to separate appearance from reality, visual alignment from physical interaction. When we say planets are in conjunction, we're describing a geometric relationship as seen from our vantage point, not a physical encounter where worlds come close to touching, or where their gravitational fields merge into some combined force. Venus orbits the Sun at about 67 million miles on average. Mars orbits much further out at roughly 142 million miles. During this conjunction, they're not actually near each other in three-dimensional space. They're lined up from our perspective, but the distance between them along our line of sight remains enormous, comparable to the space between Earth and the Sun itself. The gravitational influence that Venus and Mars exert on the Sun is vanishingly small, a fact that emerges immediately when you run the numbers. The Sun contains 99.86% of all the mass in the solar system. Jupiter, the giant planet with more mass than all other planets combined, tugs on the Sun enough to make the solar system's center of mass wobble outside the Sun's surface. But even Jupiter's influence is subtle, measured in small velocity changes over years. Venus and Mars, being much smaller and further away during conjunction, create gravitational perturbations measured in fractions of a percent of Jupiter's already small effect. Standard solar physics models, the ones that successfully predict most of what the Sun does most of the time, treat planetary positions as irrelevant to solar activity. The forces that drive eruptions live entirely within the Sun itself, in the churning convection zone where hot plasma rises and cooler plasma sinks, in the magnetic fields that those convective motions generate and tangle into increasingly unstable configurations. A coronal mass ejection begins with magnetic field lines that connect active regions on the solar surface. These field lines store energy like compressed springs, and when the configuration becomes too twisted, too stressed to maintain equilibrium, something snaps. The field lines reconnect in a violent reconfiguration that accelerates plasma to speeds of hundreds or thousands of kilometers per second, launching billions of tons of matter into space in the span of minutes. Flares, the bright explosions of light and radiation that often accompany CMEs, work on similar principles. Magnetic energy converts to kinetic energy and electromagnetic radiation in an instant, creating bursts that can increase the sun's brightness in X-ray wavelengths by factors of 10,000 or more. Plasma filaments add another layer of complexity to this picture. These structures are dense clouds of relatively cool plasma, around 6,000 degrees compared to the million-degree corona surrounding them, held aloft above the solar surface by magnetic field loops. They look dark against the sun's disk because they're cooler than their surroundings, absorbing more light than they emit. When the magnetic support fails, when those invisible field lines shift or break, the filament can erupt outward, contributing additional mass to whatever CME might be forming. Recent imagery from solar observatories shows several large filaments perched above active regions, each one a potential source of erupted material if conditions shift in the wrong way. We're currently riding the upward slope of solar cycle 26, the latest in the 11-year pattern of waxing and waning solar activity that astronomers have tracked since the 1700s. Each cycle begins at solar minimum, when sunspots and flares are scarce, and builds towards solar maximum, when active regions multiply and eruptions become routine. Cycle 26 began around 2021 and is expected to peak sometime in 2025 or 2026, which means we're either at or approaching the point of maximum activity right now. This timing alone explains why we're seeing elevated background activity, why filaments and active regions cover more of the solar surface than they did a few years ago. You don't need exotic triggers to explain increased solar eruptions during solar maximum. The sun naturally becomes more violent as magnetic complexity increases throughout its interior and atmosphere. Yet there's a thread of research, newer and far from mainstream consensus, that has resurfaced in 2025 and 2026, exploring whether planetary configurations might subtly modulate the timing or intensity of solar magnetic cycles. These ideas aren't new. Scientists have investigated planetary influence claims periodically over the past century, usually finding weak or non-existent correlations that disappear when subjected to rigorous statistical analysis. The recent papers, however, approach the question from a different angle, suggesting not direct gravitational forcing, but possible electromagnetic synchronization effects, where planetary positions might correlate with subtle variations in the solar magnetic dynamo's rhythm. Emphasis on might and correlate, words that carry heavy loads of uncertainty and speculation. These papers have not achieved widespread acceptance. They exist in that preliminary stage where ideas are proposed, equations are written, and the community collectively decides whether the ideas merit further investigation or should be filed away as interesting failures. The spacecraft that monitor the sun provide our window into what's actually happening, moment by moment. SOHO, the Solar and Heliospheric Observatory, has been watching the sun continuously since 1996, using coronagraphs to block the sun's disk and reveal the faint corona where CMEs become visible. NASA's STEREO mission placed 2 spacecraft in orbits that trail and lead Earth, giving us 3-dimensional views of solar eruptions and helping to resolve the directional ambiguity of halo CMEs. Ground-based observatories contribute optical and radio observations, tracking filaments and measuring magnetic field strengths in active regions. As of now, these instruments show elevated activity, but no confirmed major Earth-directed CME. The filaments are there, the elevated wind speeds are there, but the smoking gun of a massive halo CME aimed at Earth remains elusive, or at least unconfirmed. Some researchers operating outside the mainstream consensus invoke concepts like Birkeland currents, named after Norwegian scientist Christian Birkeland, who studied how electric currents flow through space along magnetic field lines. The idea extends to propose that the solar system operates not just under gravity, but within a complex electromagnetic circuit, where currents flow between the sun and planets, potentially creating feedback loops or coupling mechanisms that standard models ignore. These electromagnetic coupling models suggest that planetary alignments might influence solar activity, not through direct gravitational force, but through changes in these proposed interplanetary current systems. The problem is that evidence for such large-scale interplanetary currents affecting solar eruptions remains theoretical, unproven by the kinds of definitive observations that would convince the broader scientific community. Looking back through history offers some calibration for current claims. Past notable planetary conjunctions have come and gone without triggering unusual solar activity. The year 2006 saw a Venus transit across the Sun's face, a rare alignment that produced spectacular images, but no corresponding spike in CMEs. The end of 2012, infamous for apocalyptic predictions tied to Mayan calendar interpretations, arrived with planetary alignments that doomsayers claimed would unleash solar catastrophes. The Sun, indifferent to human narratives, behaved normally. These historical precedents suggest caution when evaluating claims that link planetary positions to solar eruptions. Correlation, even when occasionally observed, does not establish causation, and the human mind excels at finding patterns in random noise. But what if, just for a moment, we entertain the possibility that conventional models, despite their successes, might miss something subtle? What if there are coupling mechanisms operating at scales or through channels that current instruments don't directly measure? The universe has surprised us before with phenomena that seemed impossible until we developed the right tools to detect them. Gravitational waves were predicted by Einstein in 1916, but not detected until 2015, nearly a century of technological development bridging theory and observation. Could the planetary influence question be awaiting a similar breakthrough? Some new measurement technique or theoretical insight that reveals connections currently invisible to our instruments? These questions don't have answers yet, which is precisely why they remain compelling. The alignment is happening now. The solar activity is elevated now, and the instruments are watching now. Over the coming days and weeks, data will accumulate, either strengthening the case for unusual connections or reinforcing the standard model where planets orbit silently and the sun erupts according to its own internal magnetic rhythms. Either outcome teaches us something. Either way, we're reminded that the solar system is not a static diagram in a textbook, but a dynamic, evolving system where energy flows, magnetic fields twist, and matter hurtles through the void at speeds that would cross the distance from New York to Los Angeles in about 5 seconds. Translating space weather forecasts into language that means something to people living on Earth's surface requires bridging two very different scales of experience. When scientists announce a G1 or G2 geomagnetic storm, they're describing specific measurable disruptions to Earth's magnetic field, quantified by instruments that detect changes in field strength and direction. For most people, these numbers mean nothing until you connect them to tangible effects, to things you might actually notice or experience if you're paying attention. A G1 storm represents minor geomagnetic activity, the kind that happens dozens of times each solar cycle. If you live in northern latitudes, places like Alaska or Canada or Scandinavia, you might see auroras dancing across the night sky. Those curtains of green and occasionally red or purple light, produced when charged particles from the solar wind collide with oxygen and nitrogen molecules high in Earth's atmosphere. The particles follow magnetic field lines down toward the poles, concentrating their energy in oval-shaped zones around the magnetic north and south points. During G1 conditions, these auroral ovals expand slightly, becoming visible at locations further from the poles than usual. Amateur radio operators working in the high-frequency bands, the frequencies that bounce off the ionosphere to enable long-distance communication, might notice increased noise and occasional signal degradation as the ionosphere becomes more turbulent under the particle bombardment. Step up to G2 and the effects intensify proportionally. The auroral ovals expand further, potentially reaching northern tier United States locations, or southern Australia and New Zealand. Power grid operators in regions near the poles begin monitoring their systems more closely because fluctuating magnetic fields induce electric currents in long conductors like power transmission lines, creating potential instabilities in grid operations. These induced currents, called geomagnetically induced currents or GICs, can stress transformers and other grid components, although at G2 levels the stress remains manageable, rarely causing actual outages. Spacecraft operators take note as well, since increased particle radiation at these altitudes can affect satellite electronics and solar panel efficiency. High-frequency radio communications experience more pronounced disruptions, and some GPS position calculations might show slight accuracy degradation as signals pass through the disturbed ionosphere. Current forecasts suggest we're likely to see conditions in this G1 to G2 range over the next several days, based solely on the elevated solar wind speeds already confirmed by instruments in space. The key phrase here is based solely on, meaning these storm levels are plausible from what we already know is heading toward Earth, independent of whether any additional CMEs might be en route. The solar wind, that constant stream of charged particles flowing outward from the sun in all directions, naturally varies in speed and density. Sometimes it flows at a leisurely 300 kilometers per second. Other times, particularly when fast streams from coronal holes catch up with slower ambient solar wind, speeds can exceed 700 kilometers per second. These variations alone can compress Earth's magnetosphere enough to trigger minor storm conditions. The distinction between elevated solar wind and a direct CME hit matters enormously for forecasting. Solar wind variations produce gradual, somewhat predictable effects that unfold over hours or days. A CME, on the other hand, arrives as a discrete pulse, a compressed bubble of plasma and magnetic field that slams into Earth's magnetosphere like a wave hitting a beach. The impact can trigger much more intense storm conditions, potentially reaching G3 or higher, depending on the CME's speed, density, and magnetic field orientation. The magnetic field part is crucial because Earth's magnetosphere responds differently depending on whether the incoming field points north or south relative to Earth's own magnetic field. A southward pointing field creates optimal conditions for magnetic reconnection at the boundary of Earth's magnetosphere, opening a door through which solar wind energy can pour directly into the magnetospheric system, driving the most intense geomagnetic storms. Right now, coronagraph imagery from multiple spacecraft has not shown a definitive Earth-directed halo CME, that distinctive signature where the eruption appears as an expanding ring encircling the entire solar disk. This absence doesn't mean no CMEs occurred. It means that any CMEs that did occur either weren't aimed at Earth or were too faint to produce clear halo signatures above instrument noise levels. There's always a gap between what instruments can detect and what might actually be happening in the complex three-dimensional space between the Sun and Earth. Some plasma structures, particularly those involving filament eruptions, might not appear prominently in white light coronagraphs, the instruments that create most of our CME imagery. These coronagraphs work by detecting sunlight scattered off electrons in the ejected plasma, and if the plasma density is lower than usual or the eruption angle is unfavorable, the signature might be subtle or even invisible to current detection methods. This observational gap creates an uncomfortable zone of uncertainty. We can measure what hits Earth once it arrives, using magnetometers and particle detectors and ionospheric sounders, but predicting exactly what's coming requires catching the eruption at its source and tracking it across 93 million miles of space. Sometimes the eruption happens on the Sun's far side, invisible to Earth-based instruments, detectable only when the plasma cloud reaches spacecraft positioned at other angles. Sometimes multiple eruptions interact in interplanetary space, merging or deflecting each other in ways that alter their final trajectory and impact characteristics. The models that forecast these interactions improve every year, but they're still imperfect, still prone to surprises when reality refuses to match predictions. As elevated solar wind streams begin reaching Earth, the magnetosphere compresses under increased pressure. Imagine Earth's magnetic field as a bubble surrounding the planet, protecting it from the continuous barrage of charged particles flowing outward from the sun. When solar wind pressure increases, this bubble gets squeezed, particularly on the day side, facing the sun. The magnetopause, the boundary where Earth's magnetic field balances against solar wind pressure, can shift inward by thousands of kilometers during intense conditions. This compression sends ripples through the entire magnetospheric system, accelerating particles trapped in radiation belts, generating waves that propagate through plasma populations, and ultimately dumping energy into the ionosphere, where it manifests as auroras and communication disruptions. The seismic connection claims made by some observers deserve direct confrontation with established science. The idea that solar storms might trigger earthquakes appeals to a certain intuitive logic. If the sun can shake our magnetic field, if it can disrupt satellites and power grids, why couldn't it also influence tectonic plates? The answer lies in energy scales and coupling mechanisms. The energy delivered to Earth's magnetosphere during even an intense geomagnetic storm, measured in joules, falls far short of the energy released during a significant earthquake. A magnitude 6 earthquake releases energy equivalent to the atomic bomb dropped on Hiroshima. A magnitude 7 releases 30 times more energy than that. The electromagnetic energy transferred from the solar wind to Earth's magnetosphere during a storm dissipates primarily in the upper atmosphere and ionosphere, regions hundreds of kilometers above the ground where tectonic plates reside. Moreover, the mechanisms by which this energy might reach deep into Earth's crust and influence stress states in rocks remain unspecified in most claims linking space weather to seismic activity. Geophysicists have searched for such correlations repeatedly over decades, examining earthquake catalogs against records of geomagnetic storms, and consistently find no reliable connection. The patterns that do appear tend to be statistical flukes, artifacts of how human brains perceive randomness. When two rare events occur close together in time, we notice and remember. When rare events occur separately, we forget. This cognitive bias creates an illusion of correlation where none exists in the underlying data. Yet the question persists. Could there be unrecognized coupling mechanisms? Could magnetic field variations somehow modulate fluid pressures in Earth's interior? Or influence electrical currents in conductive rock layers, creating subtle triggers that push already stressed fault systems over the edge into rupture? The scientific community remains open to evidence, but demands rigorous demonstration, not anecdotal observations. If such a mechanism exists, it should produce testable predictions, measurable effects that appear consistently rather than sporadically. So far, no proposed mechanism has passed these tests, leaving the seismic connection in the realm of unverified speculation rather than established science. We've laid the foundation now, examining what we know about this conjunction, about solar eruptions and their effects, about the difference between confirmed observations and speculative claims. What comes next pushes further into controversial territory, exploring ideas that mainstream science treats with skepticism, but that nonetheless capture imaginations and drive alternative research programs. These are the hidden threads, the fringe theories, the what-ifs that refuse to die despite repeated failures to find supporting evidence. Understanding why these ideas persist, and what kernels of legitimate questions might hide within their speculative shells, requires us to wade into murkier waters where certainty dissolves and competing narratives fight for dominance. Every scientific consensus contains gaps, zones where observations don't quite match predictions, where models work but perhaps don't work completely, where anomalies accumulate like dust in corners waiting for someone to either explain them away or recognize them as clues to something deeper. The planetary influence question occupies one of these gaps, repeatedly dismissed by mainstream solar physics, but stubbornly refusing to vanish entirely from scientific discussion. Understanding why requires examining the hidden science threads, the studies that explore non-gravitational forces and unconventional mechanisms that might connect planetary positions to solar activity. Tidal forces represent one avenue of investigation. While planetary gravity might be too weak to directly trigger solar eruptions, tidal effects involve differential gravitational pull across an extended body, creating stress patterns that could theoretically influence fluid dynamics or magnetic field configurations. The Moon raises tides in Earth's oceans through this mechanism, and similar principles apply to any body with spatial extent. Some researchers have proposed that planetary tidal forces, though individually weak, might synchronize with solar magnetic cycles through resonance effects, amplifying small perturbations over time. The mathematics of such coupling involves complex differential equations describing how tidal stress interacts with convection zone flows and magnetic field generation. These calculations remain controversial because the coupling constants, the numbers that determine how strongly tides affect magnetic processes, appear too small in most analyses to produce observable effects. Magnetic coupling hypotheses extend this thinking into electromagnetic rather than purely gravitational realms. Planets with magnetic fields, like Earth and Jupiter, generate magnetospheres that carve out cavities in the solar wind. Some researchers suggest that these magnetospheres might create feedback effects in the solar wind or corona, perhaps through wave propagation, or current systems that link planetary magnetic fields back to their source at the Sun. The concept invokes Birkeland currents, named after Christian Birkeland's early 20th century work on how electric currents flow through space along magnetic field lines. Birkeland's ideas, initially met with skepticism, eventually gained acceptance as spacecraft confirmed the existence of field-aligned currents in Earth's magnetosphere and in the solar corona. The extension to interplanetary scales remains speculative. Proponents of cosmic electrical environment models argue that the solar system operates as an interconnected electrical circuit, with currents flowing not just within individual magnetospheres, but between different bodies through the plasma medium of the solar wind. In this view, planetary alignments might alter the geometry of these current systems, potentially affecting how energy flows from the solar interior to the corona and beyond. Critics point out that detecting such currents requires measuring magnetic fields and plasma flows with precision across vast distances, and current observations don't show the large-scale organized current systems that these models predict. Recent papers from 2025 and 2026 have attempted to revisit these questions with modern data and computational tools. One study examined correlations between planetary positions and solar cycle timings over multiple centuries, using historical sunspot records and astronomical calculations of planetary orbits. The authors claim to find weak but statistically significant correlations, suggesting that solar maxima tend to occur more frequently when certain planetary configurations arise. Other researchers have criticized these findings, arguing that the statistical methods used don't adequately account for multiple testing problems, or that the correlations disappear when analyzed with more robust techniques. This back and forth represents normal scientific discourse, the process by which ideas are proposed, challenged, refined, or rejected based on accumulated evidence. What separates mainstream from fringe in this context isn't necessarily the questions being asked, but the standards of evidence required to claim an answer. Mainstream solar physics demands reproducible observations, mechanisms grounded in established physical principles, and predictions that can be tested against future data. Fringe approaches often accept looser correlations, invoke mechanisms that require new physics without providing independent evidence for that new physics, and interpret ambiguous results as confirmation rather than continuing investigation. The line between these approaches can blur, especially during early stages of investigating genuinely novel phenomena, but over time, the distinction usually clarifies as evidence accumulates. The seismic trigger controversy exemplifies this pattern. Popular claims linking solar storms to earthquakes have circulated for decades, often gaining traction after coincidental temporal proximity between a geomagnetic storm and a significant earthquake. Websites and alternative media outlets publish lists of correlated events, creating an impression of systematic connection. Scientific rebuttals point out that these lists suffer from selection bias, highlighting hits while ignoring the far more numerous misses where storms occur without earthquakes or vice versa. Rigorous statistical tests, which compare earthquake timing against randomized storm timing, or which control for earthquake frequency as a function of magnitude, consistently fail to support the claimed correlation. One common variant suggests that solar particles might influence earthquake frequency by altering electromagnetic properties of rocks or fluids in Earth's crust. The mechanism proposed involves changes in electrical conductivity, or fluid pressure, driven by magnetic field variations, penetrating deep into the planet. Geophysicists have tested these ideas by examining whether earthquake rates increase during geomagnetic storms and find no consistent pattern. The energy coupling problem remains insurmountable in most analyses. Electromagnetic energy from a storm dissipates primarily in the ionosphere, hundreds of kilometers above the surface, while crustal stress states depend on tectonic forces operating over timescales of years to centuries, not the hours or days of a typical storm. Historical precedent offers cautionary tales about how cosmic event fears can spiral into conspiracy theories and apocalyptic predictions. The year 2012 became a focal point for numerous overlapping narratives, including Mayan calendar end date interpretations, predicted solar maximum catastrophes, and claimed planetary alignments that would trigger disasters. Books were published, documentaries produced, and genuine anxiety spread among populations primed by sensational media coverage. The solar maximum of cycle 24 arrived on schedule around 2013 and 14, producing normal levels of activity without triggering civilization collapse. The planetary alignments occurred as calculated, with no observable effect on solar or seismic activity. These episodes demonstrate how pattern recognition biases, combined with media amplification and pre-existing anxiety about technological vulnerability, can create self-reinforcing narratives detached from physical reality. Speculative physics ideas deserve mention because science occasionally benefits from wild thinking, from proposals that seem absurd until they're not. Dark matter streams passing through the solar system, unknown resonances in the solar interior that couple to planetary orbits through gravitational or torsional modes, interactions between the heliosphere and local interstellar magnetic fields that modulate solar activity in ways current models don't capture. These ideas range from plausible but unproven to highly unlikely but not strictly impossible. The key is maintaining intellectual honesty about their status, clearly labeling what's observed, what's inferred, and what's pure speculation. Why do fringe ideas persist despite repeated failure to gain scientific acceptance? Part of the answer involves human psychology and pattern recognition. Our brains evolved to detect correlations because recognizing that berry bushes grow near water sources or that certain animal tracks indicate predators nearby provided survival advantages. The cost of false positives, seeing patterns that aren't there, was typically lower than the cost of false negatives, missing real patterns. This cognitive architecture makes us prone to perceiving connections even in random noise, especially when dealing with complex systems like space weather, where many variables change simultaneously and causal chains aren't immediately obvious. Storytelling also plays a role. Narratives where human affairs connect to cosmic events feel meaningful, tapping into ancient traditions that saw divine messages in celestial phenomena. The idea that planetary alignments might influence Earth invokes this narrative power, transforming random orbital mechanics into choreographed cosmic drama with Earth at center stage. Science communicators face a constant challenge: distinguishing between legitimate wonder at genuine cosmic connections and the seductive appeal of false patterns that offer meaning without truth. So here we stand, examining claims that the triple conjunction might trigger solar eruptions through mechanisms that standard physics says shouldn't work, evaluating correlations that statistical tests say don't exist, and asking whether the scientific consensus might be missing something subtle, or whether the patterns people perceive are illusions constructed by brains eager for cosmic significance. The answer likely lies somewhere in between, acknowledging that while most fringe claims fail under scrutiny, the universe has proven stranger than anyone expected. Often enough that maintaining some humility about the limits of current knowledge remains wise. Space is far stranger than we might expect, and sometimes evidence really does surprise scientists, forcing revisions to models that seemed complete. The question is whether this particular conjunction and its associated solar activity represents such a moment, or whether it's another episode in the long history of cosmic pattern misperception. The story of solar activity and planetary alignment sits within a much larger context, a solar system that isn't isolated, but instead bathes continuously in galactic environments and occasionally encounters visitors from other star systems. Space weather doesn't originate solely from the sun's internal dynamics. The heliosphere, that bubble of solar wind that surrounds the sun and all its planets, exists within the local interstellar medium, a tenuous gas of atoms and molecules and dust left over from previous stellar generations. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent processes across the galaxy, constantly bombard the heliosphere from all directions. The sun's magnetic field, carried outward by the solar wind, provides some shielding against these particles, but the protection varies with solar activity levels and with the geometry of the heliospheric boundary. Into this environment comes 3I/Atlas, the third confirmed interstellar object to pass through our solar neighborhood, and possibly one of the most intriguing visitors ever observed. Interstellar objects differ fundamentally from comets and asteroids that formed within our solar system. Those native bodies orbit the sun on elliptical or near-circular paths, gravitationally bound to our star, recycling through the inner solar system repeatedly over millions or billions of years. Interstellar visitors arrive on hyperbolic trajectories, coming from directions unrelated to the plane of planetary orbits, passing through once and never returning. Their orbital energy exceeds the escape velocity needed to break free from the sun's gravity, meaning these objects originated around other stars, were somehow ejected or released from their home systems, and now wander interstellar space until chance brings them close enough to another star to be noticed. 3I/Atlas was detected in late 2025 by automated survey telescopes scanning for near-Earth objects and potential impact hazards. Initial observations showed unusual motion that didn't match any known comet or asteroid. Orbital calculations revealed a trajectory incompatible with solar system origin, confirming interstellar status within weeks of discovery. Since then, observatories around the world and in space have tracked this visitor intensively, gathering data on its composition, rotation, outgassing behavior, and physical structure. What they've found challenges some assumptions about what interstellar objects should look like. The object displays what astronomers call an anti-tail, a jet-like feature pointing toward the sun, rather than away from it as normal comet tails do. Regular comets develop tails because solar radiation and solar wind push gas and dust away from the comet nucleus, creating the classic tail structure that always points away from the sun, regardless of the comet's direction of motion. An anti-tail appears when dust grains ejected from the comet fall behind its orbit, creating a trail that, from certain viewing angles, can appear to point toward the sun. 3I/Atlas shows this feature, but with unusual geometry, wobbling and changing intensity in ways that suggest complex outgassing patterns or rotation states that vary over time. The James Webb Space Telescope, positioned at the L2 Lagrange point beyond the Moon's orbit, observed 3I/Atlas in infrared wavelengths during late 2025. These observations detected a surprisingly carbon dioxide-rich coma, the cloud of gas surrounding the nucleus as sunlight warms and vaporizes surface ices. Most comets in our solar system show dominant water ice composition, with carbon dioxide as a minor component. 3I/Atlas appears to have much higher carbon dioxide abundance relative to water, suggesting formation conditions different from typical solar system comets. Perhaps it formed in a colder region around its parent star, or perhaps its parent system had a different chemical composition than our own, reflecting variations in the interstellar clouds from which different stars condense. NASA and other space agencies have been quick to emphasize that 3I/Atlas shows no signs of artificial construction or unusual properties inconsistent with natural comet behavior. This clarification addresses speculation that inevitably arises when interstellar objects exhibit unusual features. The first confirmed interstellar visitor, 1I/Oumuamua, detected in 2017, triggered substantial debate because its elongated shape and slight acceleration as it left the solar system didn't quite match simple comet models. Some researchers proposed exotic explanations, including light sails or other artifacts, while others argued that natural outgassing from a comet nucleus with unusual composition could explain the observations. The scientific consensus eventually settled on natural explanations, though some uncertainty remains because Oumuamua moved too quickly through the inner solar system to allow detailed observations before fading from view. 2I/Borisov, discovered in 2019, looked more like a typical comet from our own solar system, easing concerns that interstellar objects might be fundamentally strange. 3I/Atlas sits somewhere between Oumuamua's puzzling behavior and Borisov's conventional appearance, exhibiting features that astronomers recognize but don't entirely expect in combination. This pattern suggests that interstellar space contains a diversity of objects, perhaps reflecting the range of formation conditions around different stars, or the various processes that eject objects into interstellar space. Could interstellar visitors interact with our solar environment in ways beyond simple gravitational dynamics? This question edges into speculative territory, but deserves consideration. If the heliosphere operates partly through electromagnetic phenomena, if there are large-scale current systems connecting different regions of space, then an interstellar object passing through might perturb those systems in small ways. The object carries its own magnetic field, frozen into any conductive materials in its structure, and as it moves through the solar one's magnetic field, it could generate bow-shocks or wake structures similar to what planets with magnetic fields create. These interactions would be subtle compared to the massive magnetospheres of Jupiter or Earth, but instruments sensitive enough might detect signatures of these passages. Other cosmic streams bathe the solar system constantly. Galactic cosmic rays, already mentioned, vary in intensity inversely with solar activity because the strengthened magnetic fields during solar maximum provide better shielding. Interstellar dust grains, micron-sized particles of rock and ice, and organic compounds flow through the heliosphere, driven by the relative motion between the Sun and local interstellar cloud material. These dust grains can be detected by spacecraft instruments that measure their impact velocities and compositions. The dust carries information about nearby interstellar chemistry and about magnetic field geometries in the local galactic neighborhood. Some researchers study whether variations in interstellar dust flux might subtly influence Earth's climate by affecting cloud formation or by delivering complex organic molecules to the upper atmosphere, though evidence for significant effects remains limited. The galactic magnetic field itself, that large-scale structure organizing magnetic fields across the Milky Way, influences how the heliosphere is shaped and oriented. The field isn't uniform, but has structure on scales of light years, and the Sun moves through this field at about 15 kilometers per second, relative to the local standard of rest. This motion creates asymmetries in the heliosphere, compressing it on the leading edge and extending it into a tail on the trailing edge. Whether these asymmetries affect solar activity or planetary environments remains an open question, one that requires long-term observations spanning multiple solar cycles to address properly. Historical context helps calibrate expectations about interstellar visitors. Before Oumuamua, detecting interstellar objects was predicted but never accomplished. Theoretical models suggested that every major planetary system ejects some fraction of its small bodies during formation. When giant planets migrate and gravitationally scatter millions of planetesimals into interstellar space. These calculations predicted that interstellar space should contain a substantial population of such objects. But they're faint and move quickly, making detection challenging. The advent of powerful automated survey telescopes in the 2010s finally enabled routine detection, confirming predictions and opening a new window into the composition and properties of planetary systems around other stars. Each interstellar visitor teaches us something about the diversity of planetary system formation. Oumuamua's properties suggest that some systems produce highly elongated objects, possibly through tidal disruption or collision-generated shards. Borisov's comet-like appearance indicates that volatile, rich bodies form around many stars, not just our Sun. 3I/Atlas, with its carbon dioxide-rich composition, hints at chemical variations that might correlate with parent star properties, or with location in the protoplanetary disk where the object formed. Gathering statistics on interstellar visitor properties will eventually constrain models of how planetary systems evolve and how common different formation outcomes are across the galaxy. The narrative now expands beyond our immediate neighborhood, beyond planets and solar wind and interstellar visitors passing through, into the deeper structure of space itself, the invisible architecture that organizes galaxies and determines how matter clumps and flows across cosmic history. What lies beyond the familiar realm of stars and planets and comets are structures that exist primarily through their gravitational influence, unseen by telescopes that detect light, but revealed through the motions they impose on visible matter and the distortions they create in light passing nearby. Recent astronomical discoveries have pushed our understanding of cosmic structure into territory that strains intuition, revealing components of the universe that exist without emitting light, that shape galaxies without containing stars, that make up most of the universe's mass while remaining invisible to every conventional detector we've built. These discoveries don't emerge from speculation, but from painstaking observations, from careful measurements of how galaxies rotate, how galaxy clusters move, how light from distant sources bends around massive foreground objects. The universe contains more than meets the eye, and recent work has begun mapping some of that hidden reality. Astronomers have detected what they describe as dark matter-rich but starless objects, structures that exhibit gravitational influence without the visible light signature of stellar populations. These discoveries challenge galaxy formation models that assumed dark matter and ordinary matter would always clump together, creating visible galaxies wherever substantial dark matter concentrations exist. The new observations suggest that sometimes dark matter can collect into bound structures without triggering significant star formation, creating what amount to invisible galaxies made almost entirely of the mysterious substance that comprises about 85% of the universe's matter content. Dark matter itself remains one of the deepest mysteries in modern physics. We know it exists because its gravitational effects are undeniable. Galaxies rotate too fast for the visible matter to hold them together, implying substantial additional mass distributed in halos around the visible disk. Galaxy clusters contain hot gas and galaxies that move too quickly to remain bound by their visible masses alone, requiring dark matter to supply the missing gravitational glue. Light from distant quasars and galaxies bends around massive foreground clusters in patterns that reveal total mass concentrations, far exceeding what we see in stars and gas. All these observations independently point to the same conclusion. Something is there that we cannot see directly, and it outweighs ordinary matter by a factor of roughly 5 to 1. The nature of dark matter remains unknown. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical subatomic particles that interact through gravity, and possibly the weak nuclear force, but not through electromagnetism, making them invisible to light-based detectors. Other proposals suggest axions, much lighter particles that might convert to photons under strong magnetic fields, or primordial black holes, compact objects formed in the early universe rather than from stellar collapse. Decades of experimental searches have not yet definitively detected dark matter particles, though some experiments claim hints that require confirmation. The particle's identity matters because different candidates imply different formation mechanisms and different predictions for how dark matter structures on various scales. These newly discovered starless dark matter objects were identified through gravitational lensing surveys, which use the fact that mass bends space-time and therefore bends light paths passing nearby. When light from a distant galaxy passes close to a massive foreground object, the light's path curves, creating distorted or multiple images of the background galaxy. By mapping these distortions across the sky, astronomers can reconstruct the mass distribution of foreground structures, revealing where mass concentrates even when no visible matter appears. Some regions show lensing signatures indicating substantial mass, but lack corresponding galaxy images, suggesting dark matter concentrations that failed to form significant stellar populations. Why would dark matter clump without stars forming? Galaxy formation theory describes a complex interplay between dark matter gravity, which pulls ordinary matter into potential wells, and gas physics, which determines whether that matter collapses into stars or remains diffuse. Dark matter collapses first because it doesn't interact electromagnetically, meaning it doesn't heat up or radiate energy as it falls together. Ordinary matter, mostly hydrogen and helium gas, can radiate energy through collisions and electromagnetic interactions, allowing it to lose energy and settle into the center of dark matter halos. Once sufficiently dense and cool, the gas fragments into stars. But several processes might prevent star formation even when dark matter successfully collapses. If the dark matter halo is too small, the gravitational potential might not be deep enough to pull in sufficient gas or to heat it to temperatures where hydrogen molecules break apart and allow further collapse. If the halo forms too early in cosmic history, before the universe cooled enough for gas to settle efficiently, star formation might stall. If energetic processes like supernovae from nearby galaxies or radiation from an active galactic nucleus flood the region, they might heat the gas and prevent collapse. Each of these scenarios leaves a dark matter halo intact, but without the visible galaxy that normally forms within it. Detecting these structures required advanced telescopes and long observation campaigns. The Hubble Space Telescope contributed through deep surveys that map faint distortions in galaxy shapes across large sky areas. The James Webb Space Telescope, with its infrared sensitivity, can detect faint dwarf galaxies and probe regions of space where dust obscures visible light. Ground-based observatories with adaptive optics, which correct for atmospheric turbulence, achieve sharp enough images to measure subtle lensing effects. Combining data from multiple instruments and wavelengths allows astronomers to build comprehensive maps of mass distributions and compare them with visible light distributions, revealing where the two components decouple. What do these discoveries suggest about the early universe and structure formation processes? The prevailing cosmological model describes a universe that began in a hot, dense state 13.8 billion years ago and has been expanding and cooling ever since. In the first few 100,000 years, matter existed as a hot plasma too energetic for atoms to form. Once the universe cooled below about 3,000 degrees, electrons combined with nuclei to form neutral atoms, and light could travel freely through space. This recombination epoch created the cosmic microwave background radiation, the faint afterglow that we observe today, coming from all directions in the sky, carrying information about density fluctuations in the early universe. Dark matter didn't participate in recombination because it doesn't interact with photons or electrons. It began collapsing into structures earlier than ordinary matter could, creating the gravitational scaffolding that guided galaxy formation. The dark matter structures we see today, including these mysterious starless objects, represent the outcome of 13 billion years of gravitational evolution, shaped by dark matter's peculiar physics, and by its interactions, or lack thereof, with ordinary matter. Understanding this population helps constrain dark matter's properties, and tests our models of how cosmic structure assembles. Could these dark structures subtly affect our solar system or influence solar activity? The connection seems remote because the nearest such objects likely reside far beyond our galaxy's disk, in the galactic halo where dark matter density is much higher than in the solar neighborhood. Any effect would be purely gravitational and incredibly weak at interstellar distances. However, speculation about dark matter streams passing through the solar system arises periodically. If dark matter is composed of particles, and if these particles have some small probability of interacting with ordinary matter through forces beyond gravity, then the flux of dark matter through Earth might produce rare detectable events. Several experiments located deep underground search for these interactions by monitoring ultra-sensitive detectors isolated from cosmic ray backgrounds. So far, no confirmed dark matter particle detection has emerged, though limits on interaction strengths continue to tighten. The link back to interstellar visitors like 3I/Atlas involves a different speculation, whether comets or asteroids ejected from planetary systems might carry information about dark matter distributions in their parent systems, or whether their ejection mechanisms might somehow correlate with dark matter halo properties. This remains highly speculative, but studying interstellar objects provides samples of material formed under potentially different conditions than solar system objects, offering a window into exoplanetary system compositions that complements conventional exoplanet observations. The broader narrative emerging from these discoveries emphasizes that the universe contains layers of structure and complexity invisible to casual observation. We see stars and galaxies, the luminous matter that emits or reflects light, but these represent a minority of cosmic mass and energy. Dark matter dominates the mass budget. Dark energy drives the universe's accelerating expansion, and ordinary matter constitutes a mere 5% of the total energy density. Understanding how these components interact and evolve requires detective work across multiple wavelengths and observation techniques, assembling clues from gravitational lensing, from the dynamics of galaxy motions, from the cosmic microwave background's temperature fluctuations, from supernova distances, and from laboratory experiments searching for dark matter particles. Human curiosity drives this search for the invisible, this effort to understand the universe's hidden architecture. We're pattern-seeking creatures, trying to make sense of observations that don't fit simpler pictures, where what you see is what you get. The process is humbling, revealing how much we don't know, but also exhilarating as each discovery opens new questions and new avenues for investigation. The solar system suddenly feels less isolated when we consider it embedded in a galactic dark matter halo, part of a cosmic web of structure that extends across hundreds of millions of light years. The alignment of planets that open this narrative, the solar storms, and interstellar visitors, all play out against this vast backdrop, cosmic phenomena at wildly different scales connected through gravity and light, and the flow of matter through space and time.